Welcome everyone to AI Frontiers, the podcast where we bridge the gap between cutting-edge technology and strategic business thinking. Today, we're diving deep into a fascinating development in AI reasoning. We've all heard the buzz around large language models getting better at complex problem solving. Think OpenAI's O1, DeepSeek's R10. But today's focus is a bit different. An open-source project called OpenReasoner Zero that seems to be achieving remarkable results with, well, surprising simplicity. We have a fantastic panel of experts to unpack this. Let's get straight into it. Expert 1, from a business perspective, why is this push towards better AI reasoning so critical right now?
Great question to start. Fundamentally, it's about moving AI from being a pattern matcher or a sophisticated parrot to something that can actually solve complex multi-step problems reliably. For businesses, this unlocks automation for tasks we couldn't touch before. Think complex financial modeling, scientific research, intricate logistics planning, even strategic decision support. The ROI isn't just efficiency, it's about enabling entirely new capabilities.
And that's where this Reasoner Zero concept, as the paper calls it, comes in. It's a specific flavor of reinforcement learning applied to large language models. The core idea is training the model directly from its base state using RL to get good at reasoning, skipping some of the intermediate fine-tuning steps people often use.
Directly from the base model, that sounds ambitious. What's the usual approach it's deviating from?
Well, often you'd start with a base model, then do supervised fine-tuning, SFT, on reasoning examples, maybe distill knowledge from a larger model, then apply RL. The Reasoner Zero approach suggests maybe, just maybe, RL alone, applied robustly, can get you there, potentially even more effectively if you scale it right.
And the Open Reasoner Zero paper provides some pretty compelling evidence for that hypothesis. They took the same base model as DeepSeek used for one of their variants, a QN32B model, and applied their method. The results, they actually beat DeepSeek R10 on benchmarks like AIME 2024, Math 500, and GPQA Diamond.
Better performance is one thing, but wasn't there something about efficiency too?
Exactly, that's the kicker. They achieved these superior results using only about 1/10 the training steps DeepSeek reported for their pipeline. That's a massive efficiency gain, 10 times faster or 10 times cheaper, depending on how you look at it.
Hold on 10 times the efficiency. As a business leader, that immediately grabs my attention. That drastically changes the cost-benefit analysis for developing and deploying these advanced reasoning models. Suddenly, it's potentially within reach for more organizations.
And the how is just as interesting as the what. Their approach was surprisingly minimalist. They used vanilla Proximal Policy Optimization, or PPO, a standard RL algorithm. No fancy new algorithm architecture.
Vanilla PPO. But isn't RL notoriously tricky to get stable, especially at scale? What was their secret sauce?
That's what's fascinating. It seems less about adding complexity and more about specific, perhaps counterintuitive parameter choices. They highlighted using Generalized Advantage Estimation, or GAE, with lambda set to 1 and gamma set to 1. Now, typically, values less than 1 are used to balance bias and variance or discount future rewards. Here, they went all in on long-term, undiscounted rewards.
Building on what Expert 4 said, that choice of GAE parameters, lambda equals 1, gamma equals 1, is really interesting. It basically means the model gives full weight to the final outcome, getting the answer right across the entire reasoning process. It's like telling a student, I don't care how many steps you took, only that the final answer is perfect. No partial credit along the way.
Precisely. And maybe even more controversially, they achieved stable scaling without any KL regularization. That's a common technique used in RLHF to keep the learning model from drifting too far from the original base model, preventing instability or catastrophic forgetting. They just didn't use it.
Which also ties into their reward function. It was dead simple, binary. Did the final answer and the answer tags match the ground truth? Yes, reward equals 1. No, reward equals 0. No points for trying, no penalties for bad formatting initially.
So no complex reward shaping, just a simple thumbs up or thumbs down at the very end.
Exactly. They found the model learned the required format, using think and answer tags, very quickly anyway, just from this simple success signal. It implies that intricate reward engineering might sometimes be a unnecessary overhead, or worse, as the paper hints, might even open the door to reward hacking, where the model optimizes for the reward signal itself, not the actual desired behavior.
I see your point, Expert 6, and it resonates with experiences we've had. Sometimes, the more complex you make the reward, the more creative the AI gets in finding loopholes rather than solving the core problem. It's like trying to build the perfect mousetrap. Sometimes a simple piece of cheese just works better.
So are you saying the secret here is simplicity? Just focus on the goal, use a basic algorithm tuned correctly, and let the scaling do the heavy lifting. It almost sounds too good to be true.
Expert 1, maybe it is almost too good to be true, but the data seems to back it up here. It really echoes Rich Sutton's famous bitter lesson essay, doesn't it? The idea that in the long run, the biggest gains in AI come from leveraging computation scale with relatively simple general-purpose methods, rather than complex human-designed features or algorithms.
The bitter lesson strikes again. Let's talk about scale. Expert 6, you mentioned the simple reward. What about the data scale? How important was that?
Absolutely critical. The paper emphasizes quantity, diversity, and quality. They curated a large dataset, around 129,000 samples, pulling from public math and reasoning datasets like Math, AIME, Numina, Chalou 3 Math, plus synthesizing more data. They specifically targeted harder problems and filtered out ones that were too easy or hard to auto-evaluate.
And they did something clever in the later stages for the 32B model. They actually used the model's own performance during initial training to identify the -13K prompts it found most difficult, the ones it got wrong almost every time. Then they focused a final training stage specifically on those hard cases.
That's like a personalized training plan for the AI, focusing on its weaknesses. An analogy might be an athlete using video analysis to pinpoint and drill their weakest techniques.
Exactly, it's targeted practice at scale. And the results across different data scales in their ablation studies are clear. More high-quality, diverse data led to consistently better performance and longer, more detailed reasoning chains, response lengths. There was no sign of saturation, suggesting data is a key scaling vector.
Scaling wasn't without potential pitfalls, though. The paper mentions overcoming challenges like training instability, stagnating response length, and performance plateaus. It seems their combination of vanilla PPO, those specific GAE settings, lambda equals 1, gamma equals 1, and the simple reward function provided inherent stability. Removing KL constraints likely helped focus compute purely on optimizing the policy for that final reward.
The stability despite the lack of KL divergence constraints is really noteworthy. Usually, you need that leash to prevent the policy from collapsing or generating nonsense. Their setup seems robust enough to handle the policy updates without it, which simplifies the whole process and, as they argue, might even allow for better scaling.
Okay, we've covered the impressive results, the minimalist approach, the importance of data and scale. But let's step back. Expert 5, you had a thought earlier about accessibility. Is there a contrarian take here? What's the really disruptive part?
Well, I think while everyone is rightly impressed by the benchmark scores and efficiency gains, the truly game-changing aspect might be the combination of this performance with the open source release. They didn't just publish a paper. They released the code, the parameters, the data, even model weights for various sizes down to 0.5B parameters.
Why is that so significant?
Because it dramatically lowers the barrier to entry for state-of-the-art reasoning RL. Historically, replicating these large-scale RL experiments has been incredibly expensive and complex, reserved for a few big labs. By providing a simple, efficient, and working open-source recipe, they're essentially handing the keys to the community. It's not just showing what can be done, but enabling others to do it, build on it, and innovate further.
Building on what Expert 5 said, that's absolutely right. The implications are huge. Smaller research groups, startups, even individual researchers can now potentially train highly capable reasoning models without needing massive proprietary infrastructure or arcane knowledge. This could accelerate progress across the board and shift the competitive dynamics in AI development. Think Linux moment, but for reasoning RL.
A Linux moment for reasoning RL. That's a powerful analogy. Let's also touch on some other intriguing findings. Expert 4, the paper mentioned generalization and emergent behaviors.
Yes, two interesting points. First, generalization. Even though they trained primarily on reasoning tasks, math, logic, the resulting models showed improved performance on general knowledge benchmarks like MMLU and MMLU Pro, actually outperforming the instruction-tuned version of the base model. This suggests the reasoning training enhances broader capabilities, which isn't always a given.
And the emergent behavior, they observed what they called a step moment during training, especially visible in the 7B model plots. Performance and response length wouldn't just climb smoothly, they'd sometimes jump up suddenly, suggesting the model wasn't just getting incrementally better, but perhaps unlocking new levels of reasoning capability at certain points. It's like moments of insight.
They also analyzed reflection patterns in the model's think tags phrases like wait, recheck, retry. They found that responses containing these reflections, especially correct ones, tended to be longer. This hints that the model might be engaging in something analogous to human self-correction or deeper consideration, using more thinking time for harder problems. That's quite suggestive of more complex internal processes developing.
Fascinating. It's like watching the model learn to think harder. So, looking ahead, where does this Open Reasoner Zero approach point us? What are the future implications? Expert 1, maybe start with the business view.
For business, it means potentially faster access to more capable, customized AI reasoning engines. The open nature could foster an ecosystem of specialized models. If this minimalist approach continues to scale, the cost of developing sophisticated AI problem solvers could plummet, making them viable for a much wider range of applications. We need to think about how to integrate these more powerful reasoning tools into workflows and products.
Technically, the paper lays out clear future directions. First, data scaling. They explicitly call for community contributions, hoping to build even larger, more diverse datasets collaboratively. Second, model scaling, exploring larger architectures, maybe multimodal inputs, longer context windows for more complex reasoning chains.
Third is test time scaling. This involves using more computation during inference, maybe through techniques like multi-turn interaction or using a value model to evaluate different reasoning paths, exploring the thinking space more thoroughly. And finally, scenario scaling, applying this to broader domains like creative writing, scientific discovery, even social interactions.
The underlying heuristic seems to be, if simplicity and scale work this well for math and logic, let's see how far we can push it. Can we use RL to teach models complex creative processes or scientific hypothesis generation using just a simple "is this good?" signal at the end, scaled up massively?
And the efficiency aspect remains crucial. If you can train powerful models 10x faster, you can iterate 10x faster. That rapid experimentation cycle, now potentially democratized, could lead to breakthroughs much quicker than we anticipate.
So the key takeaways seem to be: remarkable reasoning performance can be achieved with surprising simplicity using vanilla PPO and basic rewards. Scale, data, compute, model size remains king, echoing the bitter lesson. Efficiency gains are substantial, and the open source nature could be truly transformative. This has been an incredibly insightful discussion. Thank you, Expert 1, Expert 2, Expert 3, Expert 4, Expert 5, and Expert 6, for breaking down the Open Reasoner Zero work and its implications. It certainly feels like we're just scratching the surface of what's possible with scaled-up RL for reasoning. Listeners, you can find links to the paper and the open-source resources in our show notes. That's all for this episode of AI Frontiers. Join us next time as we continue to explore the cutting edge. This paper introduces Open Reasoner Zero. It is an open-source method for scaling reinforcement learning. The training improves reasoning in large language models. It starts directly from base models without prior tuning. The approach uses a simple reinforcement learning algorithm. This specific algorithm is Proximal Policy Optimization. It employs specific advantage calculation settings known as Generalized Advantage Estimation. These settings use parameters lambda equals 1 and gamma equals 1. A straightforward rule-based reward checks only answer correctness. Complex techniques like callback, labeler regularization were not needed. Callback, labeler methods often stabilize reinforcement learning training. This minimalist approach proved highly effective and stable. Performance and response length scaled steadily with training. Results improved consistently across different model sizes. OpenReasoner 0 outperformed a similar model called DeepSeek R10. It achieved better results on key reasoning benchmarks. This success required only 1/10 of the training steps. Models showed interesting, emergent reasoning abilities during training. They also displayed reflection patterns, suggesting deeper processing. The method boosted general skills beyond specific reasoning tasks. Researchers released their code, data, parameters, and models publicly. This aims to make advanced reinforcement learning research accessible. Future plans involve scaling data, models, and reasoning scenarios.